So we're going to look at a conservation of energy question. It's going to bring together the ideas of kinetic and potential energies together. And this deals with the conservation laws that we've been looking at in terms of conservation of momentum, but now we're applying it to the energy concept. And the law of conservation of energy states that the total energy of the system, all of the kinetic and all of the potential energies that are present, the total energy of the system at any point is always the same as the total energy at any other point. The difficult part is going to be considering all the various types of energy. And there are many different ways that you could have studied. We've studied kinetic energy, 1/2 mv squared. We've looked at the gravitational potential energy, mgh. There's ways to calculate gravitational potential energy from other courses. Electric potential energies we haven't covered yet, but we could. And the elastic potential energy, that's coming up shortly. And you may even remember the thermal energy, Q equals mc delta T, from chemistry classes. There's lots of different energies we can look at that try and conserve, but our main two for this video is going to be the kinetic and gravitational potential energies. I may do a video where we throw in spring energies as well in there, just to mix it up. But we're going to deal with these basic two here first. Okay, so let's apply this law of conservation of energy to what's going to be one of your very traditional type questions. You could have a skier on a ski slope. It may be a boxcar on a roller coaster track. It's going to be some type of hill with a question. Now, in these ones, by the way, it's very important in these questions that they will be frictionless until we come up to a way to accompany for the work done due to friction, which will be later on. So right now, we're not considering frictional effects whatsoever with this. So we have a skier. They're gliding along with a speed of 2 meters per second initially when they are 40 meters above the ground. So they're going with a speed of 2 meters per second. And they're going to begin to slide down this icy hill. So what's going to happen is as they're moving down this hill, their height is decreasing. They're going from 40 meters down to 25 meters. So they are losing gravitational potential energy. Their gravitational energy is being lost, but what's happening is it's being converted really, it's being changed to kinetic energy. Their velocity is increasing. So as they lose one energy, they gain the other, and the velocity vector increases more and more as they go. So we're going to quantify how we're going to do this, but all of the energy, the potential energy here before, plus its kinetic, is going to be equal to the potential energy at this point, plus its kinetic. The sum of those energies at each place will be equal. That is the law of conservation of energy. So if we're going to try and figure out what is the speed at this mystery point, we can figure that out. The before equals the after. So my kinetic energy at position 1 and my gravitational energy at position 1, when added together, has to be the same as the kinetic energy at position 2 and gravitational energy at position 2. I'll fill in the formulas for each one. So 1/2 mass times the first velocity squared plus mass times gravity times height 1 is equal to 1/2 mass velocity 2 squared plus mass times gravity times height 2. You'll notice in this question, they don't actually give you the mass of the skier. And that's because the mass is in every term in this equation, so we actually don't need it. If they gave it, we'd have to plug it in 4 times. Since it's everywhere, we're just going to cancel it out. It is an unnecessary number. So that simplifies the equation for us. So we just have 1/2 v1 squared, and then gh1, 1/2 v2 squared, and gh2. So we're trying to solve for this velocity right here. So we've got to take this term that's with it to the other side of the equation, and we're going to subtract. So you'll have 1/2 v1 squared plus gh1. Notice the masses are now gone. Subtract gh2, and that will be equal to 1/2 the velocity squared. I can simplify it more, but we'll just plug numbers in at this point just to make our lives a touch easier. So we're going to have 1/2. The initial velocity was 2 meters per second and we're going to square that. Then we have 9.81 meters per second squared is gravity, and the initial height was 40. Then we're going to subtract 9.81 meters per second squared times the second height of 25. And that will be equal to 1/2 the V2 squared. So if we plug what our numbers are going to be, you square 2, you get 4, you cut it in half. This is just 2 meters squared per second squared. Then this was 40 meters and 25 meters. I need that for my units. So then we take 9.81 times 40, you get 392.4 meters squared per second squared, minus 245 meters squared per second squared. These all would have been kilogram meters squared per second squared. However, the kilograms canceled out because we didn't have a mass, just by the way. So that's still equal to 1/2 V2 squared. Extend our page a bit. So if we work all this side out here, you'll get 149.1 meters squared per second squared. And that's equal to 1/2 velocity 2 squared. So we'll get rid of this 1/2. The 2 will come up and double. So now you will get 298.2 meters squared per second squared. That's equal to V2 squared. Square root both sides, and you get 17 meters per second as your second velocity. So what happens then is that the skier has gone, when they went from 40 meters high and they lost 15 meters of height, they gained what happens to be 15 meters per second of speed. Now that will not always be true. That just generalization happens to work in this example. You will not, every meter you lose of height, gain 1 meter per second. That's just this scenario. So don't go thinking that's a generalization that's always going to work. So now if we want to figure out at what height will the skier, now it's a part B to this question, at what height will the skier have a speed of 10 meters per second? Well, if you're 2 meters per second here and you're 17 meters per second there, there's some height in between where it will actually be 10 meters per second. And we want to figure out this mystery height at some point in between there. So let's see if we can figure out what the height will be, and we'll work our way backwards with it. So we need to set up the question again with different numbers. So I'm going to erase a lot of this. I better make that eraser bigger. Well, we'll just scoop it up. Erase it all at once. Okay, so we're going to kind of set up the same thing. We have our same formula that your 1/2 mv1 squared and mgh1, 1/2 mv2 squared and gh2. Except this is my 0.2 now. It's not 25 anymore. It's not 17. And this time we don't want to calculate v2. We want to figure out h2. So we're going to take the 1/2 mv2 squared to the other side and subtract. So we will have 1/2 v1 squared, the m's still canceled, plus gh1. We'll subtract 1/2 v2 squared, and that will be equal to g times h2. So we will have the 1/2, the v1 was still 2 meters per second. We have 9.81 times the first height of 40. Then we will have 1/2. The velocity at the second point was 10 meters per second squared, and that will be equal to gh2. So now we're going to have this 2 squared is 4, cut in half is 2. Then you still have the 9.81 times 40 is still 392.4. Then 10 squared is 100, so cut that in half, you subtract, you get 50, and that equals 9.81 times the second height. So we're now at a point we're going to be able to simplify. I'll just erase the rest of this questions left over from before. So now we're going to have over here on the left-hand side 344.2, or 0.4, excuse me, joules. We'll have to divide by that 9.81 kilogram meter, not joules, this was meters squared per second squared. and we're going to divide by 9.81 meters per second squared. That will give us our height too. And when you divide all that out, you will get left with meters. There's meters squared on top, meters on the bottom. So that will give us a height, it turns out, 35 meters in height. So you've only lost 5 meters at that point. You've gone from 30 meters of height down to, from 40 down to 35. And you've gained your 8 meters per second. So as I told you, it will not be a linear translation from height to speed. But the energy is conserved. The total amount of joules of both kinetic and potential energy at all 3 of those points will be the exact same number. And that's going to be the key for you answering a number of these different types of questions that we could throw at you, is figuring out all the types of energy that are there and trying to fill in the one missing piece in your equation. So good luck with the questions you try.